Yeah, of course you do. So we're going to be exploring complex numbers and what that means today. You'll learn before you leave today what that even means. We'll return to these standards to take a look at them in a minute here. But let's get someone to read out off the handout there at the top. And when you get to this guy's name right here, his name is Leonard Euler, or you want to be Euler. It looks like it's Euler, but it's Euler. Kirthana, you want to read for us, nice and loud? It's on your paper there too. Just that paragraph. Cool. Yeah. So I need to give you like some historical moments, and like we're gonna go big. We're gonna talk about philosophy here for a second. Okay? Is that okay? All right. So yeah. By the way, I should say something quickly about Euler. Euler is one of the most important. You should learn to pronounce his name correctly because he's one of the most important and influential mathematics and most prolific mathematicians ever to live. He's very, very well published, and he has to his name probably more formulas, more equations, more identities than almost any other mathematician alive. I have a poster over here that gives just a couple of his things that bear his name, some of the results he's discovered. And he's responsible for a whole bunch of really, really helpful notations that we use in mathematics as well. I will be one that we'll be using here. But also, he's responsible for, you can thank him for this, for our f of x notation. He's the first one to ever write functions in that way. I mean, it's not the first person maybe to think of modeling functions using mathematics. But that notation is so useful and so powerful to us, and we have him to thank, don't we? And he's responsible for lots of other really wonderful notation that you'll encounter as you go up through mathematics. So first of all, he's a great guy. He's a famous mathematician. He had this idea to include this new number I so that maybe we can have a vocabulary to describe the situation that just arose a minute ago when we encountered the square root of a negative number. So that's what this kind of, the problem this fixes, though you might not have seen that as a problem that you needed to have fixed in your life. I don't know. But let me just say this, because I think when you first meet I, you're like, the square root of negative 1? That doesn't seem legitimate to me. That doesn't feel like a number to me. But I want to make sure you understand that maybe you, earlier in your life, and certainly people throughout history, had that same reaction to negative numbers, right? Like when you first encounter the number negative 5, you think, well, that's interesting and all, but what could that possibly model in the real world? Well, I mean, if you take that view, every number is not real in that sense, right? Every number is like a fiction until we assign it some meaning in the real world. Like 3 doesn't make any sense either until you assign something. Oh, by 3 you mean like 3 people. I see. What? Okay, or whatever you're talking about. And even I think the number like negative 5, you have some real world associations with negative numbers now that make that feel very real to you, right? Temperature, or debt, or whatever else that you can think of. In physics, we often use a negative sign to indicate something going in the opposite direction, right? So yeah, charge. Lots of things in your life you understand. Negative numbers just make sense. They're very useful. There was actually a time when like numbers like the square root of 2, irrational numbers like the square root of 2, were thought to be not useful and not truly real in any sense. But I mean, they are very real in this sense. If you take a square and it has a 1 foot side length on either side, it's very easy to find the square root of 2 as you walk around. You just measure the diagonal of the square. It's the square root of 2 feet long. So it does come up naturally, and we think that root 2 is a perfectly good number too. Fractions we accept, decimals we accept, irrational numbers, negative numbers, we're good on all of those. And the reason that you accept those, I told you this is going to get philosophical, right? The reason you accept those is because you have ready examples in the real world to go to that kind of those things model, don't they? And they feel useful to you, they feel real to you. Well, I just promise you're going to take it on faith right now, I guess. But as you move forward in mathematics, I just promise that this is going to be a very, very useful number to us, I. Not only will it be useful inside of mathematics, but it will also it will also apply to real world situations, in fact, actually, and model really well things that are happening in the real world. So in no sense, even though I actually did it in a minute, in a few minutes here, we'll read another paragraph that introduces us to this by saying that this is the imaginary unit. That some people think of I as standing for imaginary, right? But I just want to make sure that when we come to that juncture and you're like thinking like, oh, we're going to talk about imaginary numbers, those aren't real. I really wish, I think most mathematicians do, I really wish that they weren't called imaginary numbers because it sets us up for that kind of thinking that like, oh, all other numbers are like real. Well, there's no sense that any number is really real. It's only the meaning we attribute to them that makes them real. So again, we're going to deal with these like quote unquote imaginary numbers today, but they're as real as any other number you've encountered in mathematics. Okay, and so we're going to expand the umbrella of numbers in your life. It's going to stretch our minds a little bit to think that there are these other numbers. And I promise it's the last stretching of your number system. It's the last number we'll ever introduce in your life until after college. This will get you this extra number we need to introduce, I, is all you'll need for the rest of high school mathematics and for the rest of all of your college mathematics if you go on to do more math in college. Okay? So, and I think, like I said, you'll find it to be very useful and very powerful and also just beautiful and interesting. Okay? So, if you haven't yet done it, answer it with your table. Make sure everyone agrees on number 4, what the answer to that is. What is I squared? Don't yell it out, but figure it out with your group. And then when you're ready, take the example in this sentence and see if you can do 5 and 6 maybe as well. Did you like my philosophy? Is that okay? All right, sorry. You're supposed to like say, all right, I think everybody agrees that I squared is what? Just yell it out. -1. It sounds like there are a couple dissensions. Let's make sure that makes sense. What is I squared? Well, by definition, apparently, it's negative. It's the square root of -1 squared. So that equals, well, I need to think about that a little bit, right? And I'm going to use, like, Michael was helping me out with this back there. What is the square root of 5 times the square root of 5? Or in general, like, what happens when you take something, the square root of something, and square it? What do you get? Yeah, in general, isn't it true that when you take the square root of something and then square it, don't you recover that inside thing? Yeah? So is that good enough explanation to justify why that should be -1? Okay? So I think that makes sense. And just so you know, the very simplest equation that we could ever run into in life that we kind of can't handle, or at least we couldn't handle until today, is this equation right here. X squared equals -1. It's the very simplest equation that kind of stymied us as recently as yesterday, right? It's the simplest equation I can think of that kind of our old techniques can't come up against. But now we have a way of expressing the solutions to this equation. What do we get? Well, just let's make sure here, because when you did x squared equals 9, what were the solutions? X equals, over here, x equals, you said, plus or minus 3. So what should the answers be here? Actually, yeah, plus or minus the square root of -1, right? That is, x equals plus or minus I. And if you haven't checked this, I just want to be clear here. I is defined to be the square root of -1. Yes? That's what we said. So when you square it, you get -1. That's That's great. But there is another number that when you square it gives you -1. And that's negative I. Both I and negative I when squared give you -1. Give it a try if you don't believe us. Okay? It shouldn't be that strange. It's happened over here too. Okay? So that solution, that equation actually does have 2 solutions. It's still true though to say that equation has no real solutions though. That's okay. All right. So let me do one of these for you, and then I'll come around. I just want to see how you guys are doing. Well, maybe actually I'll hear from a couple of you guys. I'll take some volunteers. Who wants to tell me about this first one here? Did you follow the model up here? Johnny, take it away.
Okay. Wait. Do you want me to recite it?
Sure.
Okay. Square root of -1 times the square root of 2, or I square root of 2.
Or I root 2. Yeah, I think she's right. That's a good way to write that. Do you agree? I root 2. Now, are you okay with this property, by the way, right here, that this can be rewritten, can be rewritten as that? Are you okay with that property? Yeah. That is to say, is it true that like the square root of 4 times the square root of 9, is that the same thing as the square root of 36? This seems to be the kind of property they're using here. Is it true that in general, like root AB is equal to root A times root B? You hear me on that? Does that seem to work? I mean, check this up here. Does that seem to be right? Seems right for that one example. Let me just convince you using things you already know, too. Maybe you haven't thought about square roots very much in your life. But remember the other way to write this is this, isn't it? AB to the 1/2. Do you agree? And do you agree that one of our properties of exponents that we already talked lots about is that property of exponents that we can distribute exponentiation over multiplication? So I think I've just successfully rewritten it with our exponent notation to show that actually we do know this property. Yeah? Do you agree? I just want to make sure you understand, because some of you are like, is this something, this feels new? I haven't like split radicals apart before, but you can do it. I promise you're allowed to do it. Okay? So another volunteer on this guy? Help me out there. Someone I haven't heard from yet. What? I'll come out and find you. Yeah. Yeah, so it's I times the square root of 4, which is just 2. So I think the answer there, we can just rewrite that really nicely as just 2I. Yeah. Yeah, remember this is -1 times root 4, right? I mean, the square root of -1 times the square root of 4. So that's I times 2. Yeah? Someone want to take the last one? I'll find someone who has it. Okay, you got it? Go ahead. -√10 times I. I think I agree with that. Do you guys agree with that as well? The negative, you might be concerned about the negative out front, but really, doesn't that just kind of come along for the ride? That's all David's saying. Right? The negative just kind of comes along for the ride there. Good? A I'll do for you. That's just 12I, right? Just 4 times 3 times I. B and C, have you gotten a chance to do that? I don't want to rob that from you. If you haven't done that yet, let's let other people think some more about B and C, because those are actually interesting. Careful. You'll want, as you think about these 2 problems, B and C, you may need to refer back to number 4. Think about what conclusion you made on number 4. As you answer number 6.
I really think it's too deep for my dog.
So never mind, it's not a pyramid.
I don't know.
Yes.
All right, I see a bunch of people who have these. You ready? All right, so volunteer, root 2 times I, quantity squared. Who's got that? Walk me through that one. Haven't heard from you yet today, Josiah. Go ahead. 2I squared. Talk me through that, though. How did you come to that conclusion? I think I like it, but.
The square root, alright, so the square root of 2, if you just square the square root of 2, you'll just get 2.
Okay, so you're saying we can square that individually, and we can square, like, the I individually? All right, so this is 2
2I squared.
I squared. Now, what is I squared, though? Let me push you on this. Look at number 4.
I squared.
Also known as.
Negative 1.
Good. So what's your final answer?
So it's just 2, negative 1, just negative 2.
So we get -2. Just -2 is where I want you to land on part B. Yeah? -2 is where I want you to land. Someone else talk me through C. Well, who haven't I heard from here? Have you shared yet, Ajit? Go ahead. All right.
Okay.
Wait, I think I said Ajit. Sorry.
Okay.
It's all right. Huh? Okay, so tell me what your thought process is there. Did you see that right away, or what's going on? All right, so we can do 3 times 3 is 9. Yeah, the I times I is I squared. And now I see, yeah, kind of similar logic. Yeah, I think -9 is a good answer there, too. So then the interesting question comes on number 7. Which expressions have a real number value? Which maybe you didn't see coming, but which ones do? B and C both do, right? Yeah, so I think that's interesting to think about these expressions that when you first saw them, you probably thought, oh, those are messy. Those involve like imaginary numbers. Oh no. But in the end, they're actually just, they reduce to just a single real number. We're just talking about, with this complicated expression, oh, we're really just talking about the number -2, apparently. Huh? What? Oh.
You said it didn't even matter.
Oh. Shout out to Lincoln Park. Okay. All right. So I don't know if we need to rehash these. I think we already did this, right? But so we already did these, right? I guess the one that's interesting to me is this last one, which we kind of did, but then kind of fizzled on earlier. So how do we resolve this finally here? We get t equals plus or minus, I think we wrote this earlier, t equals plus or minus the square root of -4. But now we have a new, like we said, we have a new vocabulary to write down this answer in terms of this new notation Euler gave us. Can you write it in terms of our new notation? How would you like to write that? And if you need some help, I think that you can point on your paper physically to the place where you actually already thought about what the square root of -4 should be written as. Find that place and point to it on your paper. You see it? Where's the square root of -4? You already told me. What should we write that as? Megan? Oh, yeah. 2i, yeah. Yeah, so we can write these as plus or minus 2i. Yeah? Again, it's still, I want to make sure you're clear. If someone says, I thought the answer was no real solutions, that is still correct. It's not like we're turning the tables here. The answer, are there any real solutions? The answer is still no, but we can express the non-real solutions in this new way, which is, though maybe not useful in your mind yet, is interesting. Are we having fun yet? All right, someone read, as we come to a close on this activity here. Listen up here. If you guys read as Lily reads out loud this last paragraph here, numbers. Go ahead.
Numbers of the form a plus bi, where a and b are real numbers and I equals the square root of -1, are called complex numbers. Numbers like 3i and square root of 2 times I are called pure imaginary numbers because they are made of only the imaginary.
Yeah, so we haven't seen any examples of this yet, but a plus bi is the general form where we have like something real plus something real times I. I might call this part like a number like 2 plus 3i, right? I might call 2 the real part. That is, 2 is by itself pure real. And I might call 3 the imaginary part, because 3i is a pure imaginary number just by itself. And we can mix these together, and you'll see why those maybe even arise as solutions to some of these equations. This is a solution to a quadratic that we haven't written down yet, but that could be a solution to a quadratic. And so we call numbers like this complex numbers. And like I said, that's the very largest umbrella term for our number systems that you'll ever encounter inside of high school and college. Complex numbers. So now you understand, I hope, why we've always been so careful, ever since like Algebra 1, to always say like no real solutions or whatever. You might be thinking like, why can't we just say no solutions? And oftentimes we'll accept that, I think. But you understand right now, what we mean is there's no real number that satisfies that equation maybe. There might be complex numbers though. So we have a bigger view now, hopefully, on the world. Am I right that we're making your mind expand today?
Yeah.
I told you your life would be different today. A new chapter opened.
So now the answer should be the initials NRS. No real sense.
I mean, but now we're going to pressure you to actually express them in terms of I now, too, right? So how can you determine if a quadratic function has complex, that is, let's rephrase that question, non-real zeros? How can you tell just from the graph that there are going to be no real zeros? Just from the graph. We already said it once today, but say it again. Yeah.
Go over the x.
Yeah, it doesn't intersect with the x-axis at all, right? Now there are visually speaking, there are 2 ways that could happen, and we have 2 examples before us of ways that can happen. Is that already very clear from what we just talked about? That before we even solve number 10, A and B, you already know that the answers you're going to get are going to have i's in them, yes? You should already know that from the conversation we just had about number 9. They don't intersect the x-axis. So find the solutions now. You might actually need to write down what the equations are for those. I think that's easy though. Write down the equation and actually solve the equation. Were you able to write down the equations of these guys at least?
Oh yeah.
Aren't you fancy? So set those things equal to 0 and solve.
So parallel, yeah. Paramedic. Paralysis.
All right, I think people have written down 10A. What's the equation? What's the equation we need to solve to find the complex zeros? Negative, what is it? Negative x squared minus 2, right? If someone's willing to hop up and in blue solve that, that'd be great. Did you figure out what 10b looks like, what the equation is? Maybe in vertex form? Go ahead, Johnny.
Okay.
A lot of people who know I saw it.
Plus 2 squared. Plus 3.
Alright, so is that the vertex form of that equation? Is that what you were going to say, David?
Yeah.
Right? And that equals 0. Again, we're solving for when this is going to be 0. So if you please, here in blue, solve this. Solve this now, actually, if you haven't done it yet. So actually do the solution. Find the complex zeros. Give me the i's, all that. And if you're ready, I'll take volunteers to come up and just do in blue and green if you have these. Take a look at what we get. If you haven't yet done it yourself, though, do it yourself first before you see what they're putting up there. Once you get an answer on your own paper, look up there and see if they agree with you. I haven't vetted these guys at all. Who knows? You don't know. You don't know. They might be right. Maybe you don't know. No, they're gonna work it all out for us. Do you have a different method? Do it your way. Yeah.
I still think exactly. I just open it for the I know what it is. It's finishing this way. Because then you hit the side and then
If you have a different method that's yielding results for you, please put it up too, in blue or in green.
that's just too much.
Looks like they're both using the quadratic formula here. Do you have another way? Someone out there?
I would go do
So it'll be 10.
but like 7 plus 3. Also there's 1.
Add 3. Should be 10.
But
I think it's 1.
3. Yeah.
Judging you from afar.
You need to bring it down.
No, wait.
Yeah. We have to solve
Look,
it.
you already added it. 4 plus 3 is 7.
Well, you're doing the standard.
Because it's x plus 2 times x.
Yeah.
So you do that.
Yeah. Yeah, he did. It's 4.
Okay,
X
good.
plus 4, then plus 3. I checked his work.
do you need, by the way, interesting discussion here. Plus or minus negative root 2i, do we need that? Maybe we could just say
Thank you.
that. Someone have another way of doing this? Please.
Go fix it.
If you got the same answers, I want to see. Same over here.
Did he say that?
One thing, I have a question too. This is right, by the way. Listen, guys. There's only one thing I do have a little bit of an issue with. What does this say? It says root 3i underneath the radical. But I think what you meant to say is root 3 times I. I is already the square root of negative 1. So let's just be real careful that the I doesn't slip underneath the radical.
Yeah.
Anyone have another way of doing green? Anyone have green another way? And did you get the same answer but you did it a different way? Let's see your work. I just am suggesting that the quadratic formula is like certainly always works here, but there might be a little bit of a nicer way to get it too.
Oh, wait, plus 1.
Full credit though for everything up here.
So far.
So far, until Johnny puts up some terrible mistake. We'll see. I mean, I really do mean that you can solve these any way you like, but some ways are easier than others.
Yes.
I mean, clearly we got the right answer both ways, so do what you like. But
I'd like to again.
okay, one thing we should say hopefully I should just have a little moment to do a little bit of reflection. Guys, this been good? You like I?
No.
It'll grow on you.
I like us.
Okay, it'll grow on you. It's kind of a fun little animal. We're in new territory.
Animal? I appreciate it.
No, you don't domesticate it. You'll learn to, learn to roll with it, know what to do with it. Your homework tonight is to watch a video. On Google Classroom, I just put a little prompt that said, please post a link to a video. You guys can just, search on YouTube, find any video you like on complex numbers or imaginary numbers. You can type in anything like that, or something like that. Square root of -1, type in any of those things. Find an interesting video. Either find an interesting video and post it, or watch one of the ones that has already been posted. None have yet been posted, though. If you're the first one there, you need to go find them. And then just write one comment. It says this on Google Classroom, but just write one comment. Maybe even one sentence is fine. And tell me one interesting thing you learned about complex numbers. We're going to learn lots more interesting things over the coming weeks. So some of those videos you might find are going to go really deep. In which case, watch it, but then just say something, anything you like. Let's share some interesting things we found. You can search for real world applications of complex
Let's be honest, though, in a different language, it can be more strong.
It's like practice thing where you
Like, you know how you, like, in English, like, it's like the equals.
ever give a number, it's like you can always find it.
I don't know exactly what you're talking about.
Like the time.
I don't have enough jokes.
I was like,
All you guys.
did you do the math?
Have a great day, guys. Go watch the videos. See you guys. Take it easy, guys. Have a wonderful day. See you tomorrow. Go find an interesting video. Go learn something about complex numbers tonight. What's up, Sandy? You did one. So right now, no one has posted a video. So you need to go, if you're going to go do it right now, you need to go post a link and give a comment about it. But if you get there in 2 hours from now or something, maybe you'll already need somebody who just watch it. Someone else is watching it.
Well, you haven't added me yet, so we're on.
But it's easy to find one. You can just go to YouTube, like complex numbers, or real world applications of imaginary
just
numbers.
asked.
Whatever you like. Type in complex numbers. That'd be fun. See what's going on there. Yeah, just one sentence is all. Yeah, just real little. See you soon. Yeah, Mr. Yeah. I think I've seen them all.
Kimball Tyler, please come to the main office. Kimball Tyler,